A very pleasant greeting I bid to our examiner, Dr. Zulkarnain Zaini, and our supervisor, Dr. Azizul Buang. We are from Group 13. The group members are Frederick Ching Se Chen, Kai Ziayao, Muhammad Fazli bin Sharudin, Shazani bin Abdul Halid, and Terry Selin Jomiton. For our plan design project, our group will be presenting on monetization of crude refinery and waste via pyrolysis of oily sludge and modified Solvay. Next. Our presentation will be divided into 9 parts, which are introduction, conceptual design, heat integration, process instrumentation and control, safety and loss prevention, waste treatment, plant economics, conclusion, and lastly, individual magic equipment design. Next, problem segment and objective. Next. For our case study, we were given 3 types of industrial effluent, which are oily water, oily surface water, and ballast water. These effluents contain high amount of BOD and COD due to the presence of oil, phenols, and sulfides, which can kill aquatic life by rapidly depleting the dissolved oxygen inside the water. Furthermore, the discharged material must also satisfy the limits stated in Malaysia Environmental Quality, Sewage and Industrial Effluents Regulation 2009. Other than the environmental impact and regulation requirement, the recovery of oily sludge and chloride from the industrial effluent also can be profitable by converting them into valuable products. Based on the problem statement, our objective for this project are first, to design a chemical plant to convert oily sludge and chloride into value-added products, and second, to ensure final discharge limit meet the local EQS standards for industrial effluent. Shazani will be explaining about the next part, which is the process screening.
Thank you, Fazli. Now I will continue the presentation with the process screening and overview part. The screening is split into 2 sections, namely oily sludge recovery and chloride recovery. The process are evaluated here for each of these sections. This table summarizes the pros and cons of oil sludge recovery process. The gasification reaction utilizes steam and oxygen to convert oily sludge into syngas and char at 800 degrees Celsius and 1 atm. The main advantage of gasification over pyrolysis is that it has been widely practiced on an industrial scale and proven successful. However, additional raw material required for the reaction at elevated temperature yield higher OPEX, and the additional reaction system require more equipment, which increases the CAPEX. Pyrolysis, on the other hand, does not require additional raw material in the reaction. The decomposition of oily sludge into syngas, biocrude and char takes place at 500 degrees Celsius and 1 atm. The main advantage of pyrolysis include the formation of a wide variety of valuable products. Moreover, pyrolysis grants flexibility in the product yield following market changes, which can be done by altering the reaction temperature and residence time. Perhaps the only drawback of this route is that it has not been industrially established. So the pyrolysis process will be selected for the oil sludge recovery. Next is chloride recovery. The modified Solvay reaction occurs at ambient conditions, converting brine with carbon dioxide and calcium oxide to form soda ash and calcium chloride. The main advantages of this technology include mild operating conditions and that the CO2 can be obtained from the waste flue gas, which contribute greatly to a greener road since it is designed for carbon capture. However, the downside are low conversion of salt at 35%, which may be overcome by recycling, and that it has only been proven successful experimentally in lab scale. In contrast, the industrially established road convert sodium chloride into highly valuable salt cake and chlorine at 400 degrees Celsius and 1 atm in the presence of vanadium catalyst. However, the energy-intensive step in recovering sulfur trioxide gas and the uses of hazardous components make this route unusable. Moreover, the process requires dry solid aspect, which means all the water is effluent stream must be removed, which is very unlikely. In summary, the modified Solvay route was shortlisted as the design alternative for chloride recovery. Next is the part of process flow diagram. So this is the overall process flow diagram of our design, which is separated into 3 main processes, which start off with the wastewater treatment, followed up by the pyrolysis process, and then Solvay process. Let's start off with the wastewater treatment. First of all, the oily water and ballast water goes through an API separator where the oil and sludge is separated via gravity, where oil is transported to pyrolysis reactor and sludge is transferred to the sludge holding tank. The remaining solution will then be transferred to DAS separator. In the DAS separator, the remaining sludge and oil component which has gone through percolation will then be further removed by adding air into the vessel. The sludge will submerge to the bottom of the tank and then be transported to sludge holding tank. The remaining solution will then be transported into sedimentation tank. In pyrolysis process, the sludge and oil from the wastewater treatment process goes through a reactor at 500 degrees Celsius and 1 atm to be decomposed without oxygen. The product are then discharged into a cyclone where the vapor phase containing syngas and bio-oil escape at the top stream while the solid char exit at the bottom of the cyclone and store. The top vapor stream is cooled where the biocrude is condensed and stored while the syngas is further separated to its respective component using multiple stages of membrane filter. In modified Solvay, calcium hydroxide is being used to provide an alkali-based environment for the reaction to occur in the bubble column reactor. A double ion exchange reaction occurs in the bubble column reactor where Na+ captures the bicarbonate ion forming baking soda while Ca2+ combined with Cl- forming calcium chloride as shown by equation above. Sodium bicarbonate is then filtered and calcinated to yield soda ash while calcium chloride is dried and stored. After combining the process, this would be the PFD for the overall process before heat integration is done. Now, I will pass the floor to Terry to talk about the heat integration process.
Thank you, Sezani. Hi, I'm Terry Salin Jamitol. I will explain about the heat integration part. Next. And this is the PFD after heat integration. The heat integration was conducted on only Solvay's process section, which is marked by the green square over here. Zooming in, you can see at the Solvay's unit there are 3 heat exchangers and 1 heaters with the duty of 222.33 kilowatt added to provide a complete heat integration. Next, after computing both process units, a total of 2,953.38 kilowatt energy can be saved. Then a modified simulation flow sheet was developed for the process after heat integration, and we extracted the estimated cost from the economic activation of the Aspen Plus simulation. Before heat integration, the estimated utility is 4.4 million, but after heat integration, the utility was reduced to 2.7 million with almost 50% utility reduction. That is all for heat integration. I'll pass this floor to Frederick for the process control strategy of this plant.
Next, allow me to present the design of control strategy for the plant. Each unit in the plant is sufficiently equipped with necessary control systems to ensure a safe and healthy operation of each unit while maintaining the overall plant throughput. For example, the cascade and override control scheme can be demonstrated in the reactor R201 to maintain the reactor bed level and as a safety precaution respectively. A little background here, superficial gas velocity SGV is a critical parameter that affects the health of a fluidized bed reactor. SGV is basically the gas velocity at the reactor distribution plate. A high SGV increases the fluid bed level, which increases the likelihood of forming sheet at the reactor dome, while low SGV decreases the bed level, causing reaction to be highly concentrated at the bottom section of the reactor, which tends to create hotspots or chunks resulting in a reactor shutdown. A sudden spike in temperature may indicate the formation of sheets and chunks in the reactor. Thus, to avoid such incident, an override control is used where multiple redundant temperature probes are installed at several locations of the reactor. If any of the temperature reading reaches the upper constraints, the high selector takes the signal only and sends to the override controller, which then adjusts the inlet nitrogen flow rate so that the bed level and temperature change accordingly. This safety system allows the nitrogen to bypass the heater and enter the reactor at ambient temperature, which acts as both a cooling agent and a bed level manipulator. Furthermore, a cascade control strategy is also implemented where the level controller acts as the master while the slave controller is the flow controller. The level transmitter measures the bed level and sends the signal to the level controller where a set point is specified. The level controller then calculates the error and outputs a set point for the flow controller, which then adjusts the inlet gas flow rate accordingly. Here's a snapshot of the full P&ID, which can be found in the technical report. Overall, the control systems are in place to ensure a safe and healthy operation of each equipment and the plant as a whole. I shall now invite Jared to present on the HAZOP study.
So, next slide. Next slide. Alright. So for the hazard study in this design, we selected these 3 study notes, which involve all 3 main equipments in each process, which is the DAF unit in wastewater treatment and the reactor for pyrolysis and Solvay process. Next. Here is an example of the hazard study, which is done based on the Note 3 reactor in Solvay process. In terms of flow, there are 3 possible scenarios. There will be no flow, less flow, and more flow. Each deviation will be caused by either leakage, blockage of pipeline, or failure of controller, and lead to a low yield of product. And if flow is less, an overpressure may occur if the overflow occurs. To mitigate this problem, emergency alarms such as the level alarms are to be installed and proper regular maintenance are applied. In terms of temperature, it is mostly will be deviated to either low temperature or high temperature due to the malfunctioning of controller or heater. This will bring in consequences such as the overheating of reactor and overpressure, which may lead to explosion. Emergency alarms such as the temperature alarm and pressure valves are to be installed to prevent this incident from happening. Lastly, as mentioned just now, the pressure of the reactor will increase along with the flow and temperature. Therefore, an emergency alarm such as the pressure alarm and relief valve are to be installed in order to mitigate this problem as well. Now I'll pass the floor to Terry to talk about waste management.
Thank you, Jared. Next, for waste treatment. Since this plant itself is already a wastewater treatment plant with additional function of turning waste into value-added products, there is no additional process needed to treat the final discharge, since every contaminant is below standard A and standard B, which means that this plant is good to go and able to comply with OSHA standard. Next. Meanwhile, for the solid waste coming from spent catalyst in pyrolysis reactor R201, here is the complete procedure for the solid waste management. First, the catalyst was removed from the reactor after it reaches the activation limit. The spent catalyst is then packed and stored properly in compliance with DOE guideline. The catalyst is then collected by local off-site recovery facility within 180 days. In the facility, the spent catalyst is subjected for regeneration process, and after regeneration process, the catalyst is good to go or to be sold. Next, I'll pass this floor to Fazli to explain about the plant economics of this wastewater treatment plant.
Thank you, Terry. The total purchase cost for all equipment is estimated at 23.25 million. The physical plant cost, which is 3.4 times of the total purchase cost, is estimated at 79 million. The fixed capital cost, which is 1.4 times of the physical plant cost, is calculated to be 111 million. The working capital, which is 50% of the fixed capital, is 16.3 million. Overall, the calculated total capital cost is 127.9 million with annualized cost of 8.5 million per year for 15 years. Next, the annual revenue is estimated to be 163.9 million per year. Next, the estimated annual raw material cost is 64 million per year. EP1 is estimated to be 99.9 million, while EP2 is estimated to be 97.2 million, and lastly EP3 is estimated to be 88.6 million. The total capital cost for this plant is calculated to be 127.9 million, considering the factor for fluid processing. Based on the total capital cost, the annualized repayment for 10 years is estimated to be 16.8 million per year, given that the interest rate is 5.3%. The number of operating workers for all sections is 50 people, given that 9 people works for production team, 3 people for furnace, 3 people for cooling tower, 4 person for wastewater, 12 person for electrical team, 6 workers for process control, and 10 people for quality control. The total operating cost is estimated at 84.3 million per year. The payback period for this plan is 2 years, since the cumulative net present value becomes positive after the second year of operation. The calculated return of investment of this plan is 16.06%, showing that this project is economically feasible. The discounted cash flow rate of return is 21.28%, which is higher than the minimum rate of return (MARR) which is 10%. Therefore, it can be said that this project is economically attractive as well as efficient in terms of time consideration used in the investment of the plant operation. I will pass the floor to Frederick to conclude the presentation.
To conclude, the objective of this plant design is first to ensure the final treated wastewater meets the discharge limit set by the government, and second, the recovered materials from the wastewater is to be converted into value-added products. In this case study, the industrial effluent consists of oily water, oily surface water, and ballast water contain high BOD and COD due to the presence of oil and other organic compounds. The removal of oil and suspended solid are done using the API separator and dissolved air flotation unit. The recovered oil and sludge is further processed in pyrolysis units to produce syngas, biochar, and bio-oil. Sodium chloride is also recovered from the wastewater and processed into calcium chloride and sodium bicarbonate through the modified Solvay process. Overall, this plant design achieved its objective by satisfying the discharge limit stated in the Environmental Quality Industrial Effluents Regulations 29 for Standard B. Furthermore, the computed capital operating costs are approximately 128 million and 84 million respectively. The DCFR of 21.3%, which is greater than the MAR of 10%, justifies that this plant design is economically feasible. Next, each of us will present our individual major equipment design. Allow me to begin my section in the design of pyrolysis reactor R201. Here is an outline of my presentation where I'll brief through the general description of reactor R201, followed by sample calculations for process design and mechanical design, and then illustrating the final product, which are the specification sheet and the dimensional drawing. The function of reactor R201 is to convert the waste oil and sludge into syngas, biocrude, and char. The thermal decomposition reaction is carried out at 500 degrees Celsius and 1 atm in the absence of oxygen. The reactor bed can be quenched using cold nitrogen gas. Fluidized bed reactor was selected over fixed bed due to its high contact area of catalyst and reactant, which maximizes the catalyst productivity. It also allows uniform and rapid transfer of heat and gives high stability since the pressure drop across the bed is independent of the particles. The ZSM catalyst is preferred over other catalysts due to its ability to maximize the yield of light olefins while maintaining a relatively high yield of aromatics. Besides that, it has high reactivity with low coke formation, which is desirable. For process design, the reactor dimensions are computed. For fluidized bed reactor, it is necessary to include the additional space above the dense fluid bed known as the transport disengagement height, which can be calculated based on the correlation proposed by Pauline. This assumes a SGB value of 0.8 based on literature to obtain a TDH of 4.84 meters. The bed volume is then calculated by dividing the inlet volumetric flow rate with the weight hourly space velocity obtained from literature, which is 0.35 per unit hour. The column height to diameter ratio of 7.5 is typical in industry. The column height is basically the sum of the bed height and the TDH. And arranging these relationships in the form of simultaneous equations, the diameter can be solved, which is 1.41 meters. The computed diameter is then substituted back into the previous equations to compute the column height, the bed height, and the bed area. The computed dimensions of reactor R201 is shown as follows. Subsequently, the pressure drop across the bed and the distribution plate is also computed with the following correlations. As the computed pressure drop is less than 0.5 bar, the design is acceptable and practical. Next, the mechanical design computes the necessary parameters for supporting the reactor column. Based on the design temperature and pressure, the minimum thickness of reactor wall is computed, which is 0.02 meters or 20 mm. Building on this, the head and closures thickness are computed. Torus spherical head is selected for this head design with the following correlations. The crown and knuckle radius are computed using the inside diameter and the minimum wall thickness. The computed head thickness for the top closure is 30 mm, while for the bottom closure is 34 mm, after accounting for differential pressure. Since the top and bottom closure thickness are above the minimum design thickness, the computed thickness is valid is therefore valid. A corrosion allowance of 2 mm is also added, thus giving a top and bottom head thickness of 32 mm and 36 mm respectively. Subsequently, the skirt is also designed to support the wake of the vessel. Two types of stress are considered here, namely the bending moment stress and the dead wake stress, which are computed by their respective correlations. The operating dead wake stress uses the pressure drop across the grid, while the total dead wake stress uses the pressure drop across the bed, thus giving different values. With the calculated stress, the maximum compressive and tensile stress are calculated. Since the computed compressive and tensile stress satisfy the criteria stated below, the computed skirt design is therefore valid. The reactor specification sheet and dimensional drawing is illustrated. Overall, the dimensions of this reactor is considered relatively small as compared to the typical industrial scale. Since this design statement involves only a small scale of production. I shall now invite Terry to present her equipment design.
Thank you, Frederick. Next, I will present about the reactor I'm in charge to design with, which is R301 Solvay's reactor. And here's the outline for my part. First is the general description covering the basic function and process for this reactor. Then the design methodology, where the whole procedure of designing this reactor is explained. Then sample calculation was developed to determine the dimension for this reactor. Next is the specification sheet containing all the required info for this reactor. Then finally the technical drawing of this reactor. Starting with the general description of this reactor, the main function for this reactor is to produce soda ash by scrubbing carbon dioxide with calcium oxide that has been mixed with brine. This reactor will operate at temperature 100 degrees Celsius and pressure 500 kilopascal. For the type of reactor, bubble column reactor or BCR is selected due to its high heat and mass transfer rate. And in terms of cost, BCR is considered economical for this process due to its low cost, and most important is that BCR is able to scrub carbon dioxide, which is the main reason why BCR is selected for R301. I'd say that BCR in this process has similar function to that of an absorber column, where carbon dioxide is fed into the reactor, scrubbed and reacted with calcium hydroxide, forming sodium carbonate and calcium chloride. Next. Here you can see the step-by-step procedure of designing this reactor. First is the selection of which type reactor need to use for this reaction, where I shortlisted 3 types of reactors to compare, and due to its advantages that I have explained in the previous slide, BCR is selected from the screening. Next is the data collection from high-C simulation, such as mass, flow rate, density, and viscosity for the feed flow. After data collection, I started with the calculations to determine the process design parameters, such as the volume of bubbly space, diameter to length ratio, reactions involved in the reactor, and also the optimum condition for the reaction to occur inside reactor. Next would be the mechanical design, engineering document, and cost analysis. Next. This is a sample calculation to determine the bubbly space volume of this BCR, referred from Akita and Yoshida in 1973. Bubbly space volume is the space in reactor whereby the carbon dioxide scrubbing takes place, and as well as the Solvay's process. Starting with assuming the bubbly flow rate of 0.05 meter cube per second, and after carbon dioxide inlet and removal mass flow rate calculated, we can determine the bubbly space volume, which is 85.22 meter cube. As for the dimension of the vessel body, the diameter is calculated to be 3.85 meter, and the height is 7.32 meter, and the wall thickness is 20.8 millimeter. After considering 2 millimeter of corrosion allowance, the new thickness is 22.8 millimeter. Next is the calculation for head enclosure. The head thickness is calculated to be for both top and bottom to be 0.032 meter with the shape of spherical head. And this is the specification sheet and dimension drawing for R301, summing up both ends covered by spherical heads. And as for the material, stainless steel grade 304 is used for most part of the reactor body due to its quality and affordable cost. As for the bolts, carbon steel was used as most commercial bolts made using carbon steel, hence easy to obtain. Compared to R201, R301 is much bigger in diameter since it needs to accommodate higher flow rate of feed. And that is all from me. I'll pass this floor to Jared.
Muted.
Sorry. Good morning to all. Now I'll be presenting about the equipment which I designed, which is E309 heat exchanger. Kindly find here is the outline of my presentation. First of all, I will explain a little bit about E309 for a general introduction, followed by the design methodology, where the procedure of designing the equipment is shown. Next, I will show some of the calculations which was used during the design process to determine the dimension of heat exchanger. And lastly, the specification sheets which contain the summary of the heat exchanger will be shown to you, as well as together with the drawing of equipment. First and foremost, heat exchanger E309 is introduced after the heat integration process during the design of plant. So the main function of E309 is to transfer the heat energy between the fluids from E304, which is stream 62, and F301, which is stream 57. The hot stream of this heat exchanger is in the vapor phase, and the temperature of the stream should change from 200 degrees Celsius to 101 degrees Celsius. As for the cold stream, the stream should be in liquid phase, and the temperature should change from 35 degrees Celsius to 104 degrees Celsius. Next. E309 is a shell and tube heat exchanger. As the table shown here, it shows the advantages and disadvantages of the plate heat exchanger and shell and tube heat exchanger. Even though both types of heat exchangers show off their own perks, in the end, E309 is selected to be a shell and tube heat exchanger due to the lesser disadvantage compared to the plate heat exchanger. Furthermore, the plate heat exchanger are mostly used for regeneration purposes, which are mostly ideal for the industries such as the food and beverage. Furthermore, E309 is selected to be the counterflow heat exchanger as it has the highest rate of distributing heat compared to the other type of flows. So now we will move on to the design methodology of the presentation. The first step to start off the design is to determine the type of heat exchanger which is compatible for the process. Next, we will start with the process design of the equipment, where we will gather the data from the simulation for PDP1 and undergo calculations for the components of the equipment, where I will show you a few examples later on. After process design is done, the mechanical design of the equipment such as the bolt, nozzle, joints, and vessel support for the equipment are calculated and designed as well. The last calculation for the equipment will be the cost of equipment, which will be determine the capital cost of the plant. Lastly, engineering documents such as the specification sheet and the drawing of the equipment is done as well. So kindly find here are the sample calculation for the process design stage for E309. Here is the summary table for the data which is being used for the calculations. First and foremost, we start off by determining the log mean temperature difference correction factors, which can be shown here along with the log mean temperature. And after obtaining the R and S value, we can refer to the graph in the Chemical Engineering Design Volume 6. The F value can be obtained and find the final TM value. The heat transfer area can be obtained via this equation as well, which is 23.165 meters squared. Next. After obtaining those data, we made assumptions for the heat exchangers such as the table shown here, which will be used for the tube and shell dimension calculations. First of all, we can calculate the tube section, which consists of the number of tubes, cross-sectional area, and total flow area, followed by the bundle diameter and shell diameter for the heat exchanger. Next, we can then calculate the tube side heat transfer coefficient and pressure drop, which is in this case are 927.337 watt per meter square Kelvin and 13.076 kilopascal. The shell side heat transfer coefficient and pressure drop are calculated as well with the same formula shown in the tube side. So that's the sample calculations for my process design of my equipment. Next. So shown here is the specification sheet for E309 along with the data that we calculated for equipment along with the data of hot and cold stream of the heat exchanger. Next. Okay, finally, here is the drawing of my equipment E309, which includes the internal view, side view, and top view of the heat exchanger along with the measurement details at the sides. The nozzle design is also included inside the drawing as well as the measurements. So we have reached the end of my presentation. I will pass it on to Shazini to talk about his cooler. Thank you for your time.
Thanks, Kaizayo. Now I will continue the individual part by explaining the minor equipment that I had chosen, which is cooler C2O2. The C2O2 cooler being used to cool down the hot product from the cyclone S2O3 from 500 degrees Celsius to 120 degrees Celsius before it is fed to the condenser E206. The reason why shell and tube heat exchanger being chosen among others because first, it is less expensive compared to the plate cooler. Then this kind of type are simple to disassemble for maintenance purpose and also provide a large surface area in a small volume. Here is the illustration of the cooler C2O2 where the hot stream gas feed will enter with the temperature of 500 degrees Celsius and left the cooler at the temperature of 120 degrees Celsius. Meanwhile, in the cool stream, cooling water will enter the cooler at 25 degrees Celsius and left the cooler at the 95 degrees Celsius. Next, this part will be explaining about the design methodology where it will consist two parts which are process design and mechanical design. In the process design, it will start off with getting all the condition parameter from the high heat simulation. Then heat exchanger dimension will be calculated. After that, the heat transfer area will be calculated, followed by tube side and shell dimension. And the last one to be calculated in the process design is the overall heat coefficient. On the other hand, the mechanical design will be started by doing the selection of material where stainless steel type 3 or 4 had been chosen. After that, the design pressure, design temperature and design stress will be calculated, followed by computed the shell thickness. The last part in the mechanical design will be the calculation of design head dome and design vessels subject to combined loading. Now, I will continue the presentation with the sample calculation part where I will explain briefly three chosen calculations which are heat transfer area, overall heat transfer coefficient and shell thickness. For the first calculation, the overall coefficient will be first assumed by searching it in the literature review. The value of heat transfer area that had been calculated is 7.277 meters square. Then, the overall heat transfer coefficient will be calculated by considering the parameter that already been computed in the process design and the value of it is 50.17 watt per meter square degree Celsius. And the last one, based on the design temperature and pressure, the minimum thickness of shell is computed, which is 2.5 mm. On the right side is the specification sheet of the cooler C2O2. The dimensional drawing is illustrated because the flow of the hot and cool fluid is quite small. The dimension of the heat exchanger are deemed a bit small when comparison with the normal industrial size. I think that's it for me. I will pass the floor to Fazli.
Thank you, Shazani. The design of heat exchanger E303 will be presented by me, Muhammad Fazli. Next. The methodology for designing heat exchanger E303 consists of selection of heat exchanger, the process design of heat exchanger, mechanical design of heat exchanger, engineering documentation, and lastly the calculation of cost. Next. Hello, Fred.
Yeah, computer lags, right?
The selection of the heat exchanger type is done based on three criteria which are the type of heat transfer process, the construction type of the heat exchanger, and the flow arrangements of the cold and hot fluid. Indirect heat transfer process is chosen to prevent the hot and cold fluid from mixing, which could affect the quality of the final product. Tubular design is selected because of its versatility and suitability for heat transfer between liquids. Counterflow arrangement is used for this heat exchanger since it gives the highest efficiency of heat transfer. Next. For the shell side, which are for cold fluid, the entering fluid temperature is 25 degrees Celsius and the outlet temperature is 150 degrees Celsius. As for the tube side, the temperature of the entering hot fluid is 250 degrees Celsius and the exiting temperature is 30 degrees Celsius. The log mean temperature difference after correction factor has been applied is 16.95 degrees Celsius. By assuming the overall heat transfer coefficient to be 800 watt per meter squared degree Celsius, the calculated area required for the heat transfer is 18.705 meter squared. The number of installed tubes for the heat exchanger E303 is 128 and each tube has the surface area of 0.151 meter squared. For the shell part, the calculated surface area is 0.015 meter squared with equivalent diameter of 0.014 meter. The heat transfer coefficient for tube and shell is 59.07 and 1540.57 watt per meter squared Celsius respectively. The overall heat transfer coefficient, considering the effect of fouling, is calculated at 44.91 watt per meter squared Celsius. The thickness of the cylindrical shell after taking corrosion factor into consideration is 3.85 mm. As for the head and closure, torus spherical shape is chosen because it is the most economical choice. The thickness of the head after considering corrosion factor is 5.238 mm. The total weight of the vessel, which consists of the weight of tubes and shell, is 1905.09 Newton. The dead weight stress of the heat exchanger is 0.359 Newton per millimeter squared. The thickness of the flange is 0.044 meter. The specification sheet and dimensional drawing is illustrated. Overall, the dimension of this heat exchanger is considered small as compared to typical industrial scale, since the flow of the hot and the cold fluid are relatively small. And with that, we have come to the end of our group presentation. Thank you for listening. Now we will move into the Q&A session.